I'm Léon Huet. I am a 2 years PhD student from IMPMC, the Institut de Minéralogie, de Physique des Matériaux et de Processus chimiques. And so it's one of the Institut of Sorbonne Université. And I'm also financed by the Institut of Sciences et Calcul des Données, also at Sorbonne Université. And I am talking a little bit about chemistry and about also how to train stochastic model on chemistry data in order to try to calculate the kinetics of these reactions. So yeah, so here the purpose of the thesis is to study the kinetics of chemical systems that are of interest for the appearance of life on Earth. So it's a domain that we call probabilistic chemistry. And for that, I have some tools. So to model my system, I use ab initio molecular dynamics. And then to try to sample high energetics, so the transient state of my system, I use unknown sampling method, so always in an ab initio molecular dynamics system. And then from the data out of this calculations, I will try to train a generalized non-trivial equation model in order to calculate the kinetics of my system. So here, just a little words about the chemical system I'm studying. So we can separate in two sets. The first set is a benchmark system. So here it's a very simple reactions in solution. So as you can see, it's what we call a nucleophile substitution. And it's just a metal, so a carbon that is passing from one fluorine to the other. So there is a charge transfer between this reaction. And it's a reaction that has a very high energetic curve. So that you can see here, it's in kBt. So you have a 32 kBt high energy barrier. So you cannot hope just by modelizing your system to make it react spontaneously. You have to force the system to react. And it's the same type of problem with real concrete systems. Here you have some interesting system for the appearance of light. It's the synthesis of lighting. So here you have on the device. Do you have a laser pointer?
Oh yeah,
oh, yeah,
just there. Yeah. But you need to put the USB on the. If just for the laser, you don't need it. Perhaps there is there is a stick.
Oh yeah. Okay, why not the stick?
Yeah, it's always there.
Okay, so here you have the glycine. And so here from just minerals, you can try to find a way to synthesize the glycine just by forcing the system to react. And you modelize it in a box with a repeated catalytic boundary conditions. And you add hundreds of water molecules around that you are also treating as a normal water molecule, so with quantum chemistry. So it's a really expensive calculation. And so for the rest of the conference, I will only focus on the benchmark system because I'm developing tools, so I'm still at that level for the moment. And so for this benchmark system, I have rather interesting things to say. And the first I can say is that I already have a good collective variable, which is a negative one, which is well known, which is the difference of distance between the carbon and the fluorine. So here I have D2 and D1. I make the difference in the delta D, which is a good collective variable of that system, and what has been well studied in literature. And from that collective variable, I can try to calculate the free of the data in the system. So to analyze it, for technical details, I use the GFT at the PB0. I perform born Oppenheimer molecular dynamics. It's not a long one. I'm using the CPMD software for those who are interested. And I have also 100 water sites, so approximately 300 explicit atoms. That makes 900 degrees of freedom. It's rather large. And I have one counterant also in my system of potassium. So that system, I will make it pass through a large flow chart, a large protocol. And so, yeah, there is a lot of details in this slide, but I will simplify it by saying it's a 4-step process. So first you have initialization, while you prepare your box, your modelization box. Then you isolate the local minima of your system. Then you isolate the transition of your system. And then you try to quantify the frequency curve of your system. That's four-step process. And for the rest of this presentation, I will only focus on two steps of this large process, because this step that I use to generate data that I can use to train a GE model. So this step here is transition path sampling. And this step here is for quantification. So it's you need more information about transition path sampling to create it. And it's umbrella sampling. And I will detail these two steps, what it consists, and how I can use the data out of it. So first, transition path sampling. So transition path sampling, it's a globally a generative protocol of new transition path of new transitions. So first, you need an order parameter. So you need a variable that distinguish the two states of your system. So the reactive and the product, the reactants and the product. And you need one reactive trajectory. And what you do is a really three-step process. You select a random geometry from the trajectory you have. You launch two dynamic with opposite speed from that new geometry. And if you obtain a transition, you validate this new transition that you're not doing the test. That's all. And like that, you generate a lot of transitions like that. So you have a data set of your system that is concentrate of transitions only. So you can modelize it like that, because when you launch two dynamics, you have a backward and forward, and you can reverse time of the backward one to create a unique trajectory that goes directly from the reactants to the products. So the advantage of that is that as it's a modernization, I can show it to you. So I will now show it to you in a small video. So as you can see, it's a little accelerated. But here you have the two chloride and the carbon. And at one moment, the carbon passed from one chloride to the other. So I have accelerated a lot. But in fact, it's accelerated compared to what I observed when I put it in my system. But here it's a 3 picoseconds length of trajectory. So it's rather short, in fact, normally. Okay, let's go back to the presentation. So, no, sorry. Okay.
So yeah, does the order parameter need to be continuous, or can you just be a non-specified state A and state B?
In fact, when you define state A and state B, you can create a continuous variables that goes from 1 to 2, and that distinguish between A and state B, and that's what we do generally. Okay, so it gives us agnostic data about the transition state, because each random coordinate geometry I have validated with this protocol is a good candidate for a transition state. That gives me unbiased data of the transition, because there is no bias in the data. So I can try to study a lot of different collective variables out of this data, and to see if they are good to study this transition. And the trajectory I create converge toward the minimum pre-energy pathway. If I begin my algorithm of generation with a extension that does that, for example, that is very far from the minimum pre-energy pathway, then iteration by iteration, I will converge with toward the center of the image here. But the problem is that it's not of the data, and it's a big problem to find after train a generative model. And the second data set is umbrella sampling. So it consists in multiplication of your system. So you create copies of your system, and for each copy you add different external bias to force it to sample the high energetic state of the system. So here, for example, you have 5 replicas, but I'm more using 50 to 60 replicas. And for each system, so you sample the bias system, and then by retiling the bias at the end, you can recreate the full free energy curve of your reaction. So it's a more complicated step because you need first a reaction coordinate. So it's you need really something that helps that contains inside it all the mechanism of your system, and also you need a good first trajectory, so trajectory which is not far from the minimum free energy pathway, in order to launch the sampling. APQ bias trajectories. So for in the objective to train a generative model, it has to be corrected, but the trajectories obtained are stationary, and you can obtain the free energy curve, so it gives you more information about your system. Okay, so I have 2 data sets. And the simple question is, how can I extract kinetics out of it? And so the two steps we propose in the team is to first train a dynamic model out of this data set, and then calculate the kinetic directly out of the model. And that's not really simple. So we decide to focus on a very specific type of model, which is a generalized random equation. So it's a dynamic model, which is composed of 3 terms as the classical non-linear one, but the one which is different to ground point is the memory kernel. So it has the memory into the system. So for example, if I have here a trajectory which is evolving 2 times, I can try to parameterize all these terms and extract all these parameters and fit all these parameters on this curve, and then try to generate after to extrapolate my data through time. And okay, so I will focus now on the memory channel. So the memory channel is like an augmentation, an improvement of the friction. It's okay. Sorry, just need to find another word. Okay, the memory channel is like a friction which has a decay time. Okay. Can I use maybe this? Oh.
You know, but the erase this.
Yeah.
And you have 10 minutes left for you talk.
Oh, that's very fast for me.
Yes. Thanks.
Okay, so very shortly, when my system is here at the beginning and when it pivots, here it's time. Here it is at the moment it's so okay. You know what? I will show it to you after in the presentation because I have just 10 minutes. Okay. So first, what I can say about my system is that the transition is really short. It's 100 femtoseconds. And when I try to calculate the memory of my data when I'm just in the reactance state, I see that the characteristic time of my memory is the same order of magnitude. So that means that I can't take a simpler simplest simplest equation to modelize my system, because I have memory effect during the transition that can create recrossing or other type of effects. The other problem I have is that if my Hamiltonian is time reversible, the GLE is not. So here, when I look at this trajectory here, there is something really interesting that happens just at this moment. Because at that moment, my force tells me to stay in the reactance. My friction tells me to stay in the reactant part. So it's my noise that makes me jump the barrier. So I can't use time reversed data. So I need to transform my data set into this one. And here it's much more difficult because I have just trajectory that falls from the barrier. And it's like a good analogy is throwing a stone in a pool of water and trying to know just by looking how the stone is falling, how much time it will take to take it back in my hand. And that's a really good analogy because my system is not thermalized. You know, when my system is falling out of my variable, so here it's my predictive variable. So here I am at the transit state. And when I'm falling, I'm going out of a normal distribution of the speed. And that's a big problem because when I want to extract the mean force of my system, usually I do mean value of the acceleration, which is at equilibrium equal to the force. Normally, the mean value of acceleration conditionate on the values of the collective variable is the mean force. But here I can't do that because if I do the mean value of the acceleration here, I have a constant term that comes of the memory kernel. And that's approximately at that moment, we decided to not do that. We decided that the transition path sampling data was not good ones to train a generative model. We tried many other things we can discuss in more details, but yeah. So we decided to pass from the transition path sampling data to the umbrella sampling one. And here you can see big difference. So here is a density map of my system. So here you have the carbon, here you have the two chlorine in green. You don't see that, but sorry for that. And you have clearly you can see the solvation sphere, and you can see that my solvent has much more converged and exploit the system in my umbrella sampling data. And that's good news because that means that maybe I can extract out of the umbrella sampling data the behavior of my system, even if it's bias trajectories. So as the system is stationary, I don't have anymore this problem of unconverged speed. But I have an effect of the bias on the memory kernel. So as you can see here, I have in the reactance state, I have a trajectory which has no bias, and then trajectory here in orange that is biased. And here I have the two of them, and as you can see, the memory kernel is pretty close to each other, but slightly different. And we can guess that this difference is much higher when I am at the top of the barrier. But as I don't have any converged data at the top of the barrier, I can't show it to you. I'm sorry. What I can say also is that the memory kernel is very different if I am in the reactant part and at the top of the barrier. I have much less friction at the top of the barrier. So I need to take that in account in my system. Okay. So here it's the development marks. It's here I stopped my works. And I'm at that moment trying to put some hypothesis. The first hypothesis I want to put, because it's really hard to deal with, is that the effect on the bias on the memory kernel is negligible. And the second one is that the memory kernel and the noise, which is linked to the memory kernel, must be positively different. And so I have two propositions. I can recompose the GLE. So take the force of the umbrella sampling by out of the free energy curve, and take the memory and the noise from each US window, so umbrella sampling windows, and just perform a linear regression on all the US umbrella sampling windows to create a position-dependent memory kernel. Or I can do all at once, directly in the reference of the memory kernel position-dependent, correct the bias during the inference. And then a small word about what I can do after. So after I have a good inference of my system, which is not the case today, but let's hope. I have many methods to directly estimate the kinetics. So the sign and this one, or the Cramer's theory, which is little older, but to prepare with, I can try. And I can also try to brute force the kinetics. Because as I am in a model system, I can increase the temperature a lot. And so I can create a curve of the evolution of the kinetics with the temperature and try to extrapolate it to the normal temperature system, which is the one I'm modeling. Okay. And that's all for my presentation. Here is my references. So I want to thank, of course, Léon Huet, which is the postdoc I'm working with and which is helping me with all the technical parts about you. And yeah, thanks for your listening. And I'm sorry, I'm a little late, maybe.
No, you're.
Oh, perfect.